Okay, so Evgenia was speaking about star-planet interactions, and now we're moving on to a different kind of star-planet interaction, specifically those that lead to auroral emissions, potentially detectable from extrasolar planets, which include radio, UV, H3+, and so on. And to guide us through this, we have principal scientist at JPL, Jospeh Lazio. Joe has basically been involved or led almost all of the efforts, I think, in some capacity that are ongoing for detecting radio emission at low frequency. He's been involved from the get-go in efforts in the US and elsewhere, and I think he has a very good perspective on the radio possibilities for X-band detection. And I think one of his primary goals in his efforts to pioneer low-frequency radio has been the detection of radio emission from extrasolar planets. So, take it away, Joe.
Thanks for the kind introduction, and it's good to see everybody here and enthusiastic about this topic. And of course, as in all science, this is not being done in a vacuum. I owe a tremendous debt to many people with whom I've had interactions in putting together both this talk and much of the work that you'll see, or some of the work that you'll see presented. Okay, Wes just summarized the status in terms of extrasolar planets into astronomical accuracy. We have something like 1,000 confirmed, and then something like another 3,500 planetary candidates, though as Wes suggested, there's good reason to suspect that many of those are real. Most of those, contrary to these wonderful pictures that NASA puts out, most of those are actually indirect detections. This is what might appear, say, in the New York Times or in some popular astronomy magazine. But of course, what we actually get in terms of data are something like this. This is a radial velocity curve of a star, and I've picked it for no other reason that I could find it easily. There's nothing particularly outstanding about this, but of course, again, what you're seeing here, all these data are simply a change in the velocity of the star as it's moving back and forth in response to the gravitational tug of the planet. And this is a transit light curve, not unlike what, say, Kepler has produced, where again, you see that the star brightness is constant for a while, and then it exhibits this characteristic drop and recovery, consistent with some dark object moving in front of the stellar disk. And these are, again, remarkable. Remember, certainly when I was growing up, we knew of no planets outside the solar system. And at some level, we really do live in a very special time in human history, because we've gone from speculation about planets outside our own solar system to real hard data. But I think moving beyond, or trying to get closer to this sense of actually understanding these bodies as real objects, as opposed to, say, just points on a radial velocity curve or a transit, we really need to go into the characterization. What can we say about properties? And Wes showed some of that, right? Mass, radius, ultimately perhaps aspects of the atmosphere or deep interior. And I'm going to attempt to argue that planetary magnetic fields are at least one way. They may present a way of detecting, and they potentially represent a way of characterizing, although somewhat like Evgenia, I was a bit sobered by Dave's earlier comments as to the extent to which we might really be able to use, but I remain somewhat hopeful. In one of the talks this morning, either Jerry or Dave's talk, he flashed up a slide that showed that the magnetic field of the planet extends well outside the planet. And I hope you can see this, but here's a hypothetical, well, here's a notional planet, and if you can see these red lines, these are the magnetic field lines of the planet. In the case of the solar system planet, the magnetic field can extend, or the region of influence can extend several to tens of planetary radii outside the planet. If the planet was, in some sense, isolated, the magnetic field would extend out and form sort of a spherical region around the planet. But the planet is very often immersed in the stellar wind, or the solar wind in the case of the solar system planets, where there's this high-speed stream of particles flowing off the stellar surface, and it carries not only their particles coming off, but those carry magnetic field. And those interact, and the result is that the magnetosphere, somewhat misnamed magnetosphere, is then distorted and stretched into this sort of teardrop shape. So again, if you can see these field lines, instead of being nice regular dipolar lines, they start getting stretched into the distance there. And these are these can be, the magnetospheres can be extremely large objects. If you have very good eyesight, I think you can resolve the disk of Jupiter. But if you then go out and look at the night sky and you see that little pinprick of light that's Jupiter, the actual magnetosphere is something like 5 times the diameter of the full moon. So these are, in some sense, the largest structures in the solar system. And one of the questions now is, can we use these either to detect extrasolar planets, or discover actually in some cases, and certainly can we use these to study? And one other aspect, this is of course a 2-dimensional representation. Keep in mind that these are really 3-dimensional structures, so you have to imagine rotating them in 3-dimensional space, but they're very large structures, certainly in the case of, and they stretch very far back. One of the interesting factoids is, for instance, the moon can pass through the so-called magnetotail of the Earth, and there's been at least one case in which it appears Saturn actually moved through the magnetotail of Jupiter. So again, the magnetic field can have a significant influence in the region around the planet. Okay, so here's again this 2-dimensional picture, a representation of a magnetosphere. We have this stellar wind that's moving in, and the stellar wind therefore provides an energy source, and there could be a couple of different ways in which it does this. One is the actual kinetic energy of the inflowing particles, and the other is because the stellar wind also carries a magnetic field, or can carry a magnetic field with it. It could be the magnetic energy contained in the stellar wind or in the plasma. Again, to astronomical accuracy, something like 1% of the energy that is being carried in by the stellar wind can be converted, and I'll illustrate this in a little while, into UV emission from the auroral regions, the magnetic auroral regions, so where or magnetic polar regions. And as we also heard today, or earlier this morning, Mike Werner pointed out that in fact there might also be infrared emission, although I have nothing on that in this presentation. And then again, to something like astronomical accuracy, about an equal amount of that input energy is converted into radio emission. If you imagine zooming in, then in an observational sense to these polar regions, this is an example of the Earth, and a while back there was actually a pair of satellites called the Dynamic Explorer, or Dynamic Explorer 2. This is the ultraviolet aurora, or ultraviolet auroral oval above the Earth's, one of the Earth's poles, north or south, I don't remember which, and then these tracks indicate where where the satellites or the spacecraft were actually able to detect radio emission as energetic particles or electrons were streaming down these field lines into the polar regions. Perhaps a more photogenic example comes from Jupiter. Here is HST ultraviolet observations of the magnetic polar region, I think the north polar region of Jupiter. You can see here are tightly constrained regions where the electrons are flowing in and exciting ultraviolet emission. What you don't see in this one is, of course, the radio emission that's being generated, but that's also one of the topics, or one of the key missions or key outcomes expected from the Juno mission, is that it will be able to pass through some of these magnetic polar regions and actually make in situ measurements. You can see that there's not only this oval region, such as in the case of the Earth, but there are also bright spots. One of them is due to a magnetic flux tube that connects out to Io, and we just had a bit of discussion about the fact, even though Io itself may not have an intrinsic magnetic field, it can still generate, or it can stimulate in some sense, emission from Jupiter. And then there are weaker ones, let's see, from Ganymede and Europa as well. Let's start now from an observational standpoint. How could we detect some aspect of this over interstellar distances? And we're going to start with actually the magnetosphere itself. Is the magnetosphere itself detectable? This somewhat busy plot shows, first off, in the green, it shows the optical transit curve, or the visible wavelength transit curve from WASP 12b. And again, this is very much the case if you just think of, for the moment, just think of there's a dark spot moving across the disk of the star. The other points that you see plotted here are measurements of during the same time in the near UV. And what you see is that the near UV points display a different light curve than the visible wavelength. And there are two aspects about it. One is that the light curve is, well, first off, it's wavelength dependent. It's different between the UV and the visible wavelength. It's also asymmetric. You notice that, for instance, these UV points, they're somehow indicating that in the UV, the transit is effectively starting before it starts the visible wavelength. And if you think about just the cartoon picture, start with the visible wavelength and start with just a pure rocky ball. Here it is as the planet is just approaching the stellar disk. You would expect a drop in the brightness of the star as the planet starts to begin its ingress, which is this part here, and then it goes across the disk, and then there's the egress where the planet is now moving out from in front of the stellar disk. Now the wavelength dependent part of a light curve is actually not that difficult to explain. This is the toy model case, or the conceptual case of if you have a rocky ball. But if you have an atmosphere, depending upon the characteristics or the composition of the atmosphere, you could have a wavelength dependent. But that would not immediately lead you to think that the light curve should be asymmetric. And in fact, if you think that the planet has some kind of atmosphere, what you would naively expect is that as the planet moves this way, the atmosphere might trail behind it somewhat like a comet if it was being evaporated off or blown off somewhere. And it seems very difficult to explain this from an atmospheric standpoint. However, in this picture, if you can see, of course, in what I fear is a near invisible blue, out here there's a bow shock. The stellar wind is flowing in, and the particles begin to interact with the magnetic field of the planet. The incident stellar wind is flowing in so quickly that this interaction cannot be transmitted upstream. The particles are moving in supersonically, and therefore you set up a shock wave here. For the benefit of the students, any students in the audience, I'll point out that this is similar in concept to the shock wave that you might expect, say, from a jet fighter or the now dearly departed Concorde, in that there's a rapid change in density here. But it's distinct from the case of a jet plane. Here, the jet plane is actually moving through and colliding. I mean, the surface of the jet is colliding with the particles in the air. Whereas in the case here, there are no actual physical collisions between, say, particles, but it's the interaction between the particles and the electromagnetic fields. Okay, that produces this rapid change. It sets up a bow shock. This bow shock will be dynamic. Dave indicated earlier this morning that the magnetic field of the planet itself could change. But in addition, for instance, if any aspects of the stellar wind change, and we certainly see that in the case of the sun, it occasionally emits plasma blobs, which we call coronal mass ejections. And as well, if the planet itself is in an eccentric orbit, then it will move farther and closer, exposing it to different levels of stellar wind. Here again is this this conceptual picture of if you have just a rocky planet or a ball that's moving in front of the disk. But suppose this thing now has a magnetosphere surrounding it, and the stellar wind is flowing in at such a level to actually set up a bow shock that could potentially lead, or in fact, Aline Vidodo and collaborators have suggested that could increase the UV optical depth, and that would potentially be in front of the planet. This movie illustrates it perhaps better than I can say it. Here's the stellar disk. Here is the optical light curve, or visible wavelength light curve. And now, as I start the movie, what you'll see is this little trace is illustrating the location of the planet. And in a moment here, you'll start to see this little faint trace. This is the magnetosphere bow shock. Here's the planet actually moving in. And at least in this particular model, they can replicate that if the planet has a sufficient magnetosphere, it will explain this asymmetric wavelength-dependent light curve. Now, there is a bit of a complication in that this is the case for WASP-12b. My understanding is there's another object, TRES-3b, that does not show this effect, although one might expect it to do so. So it's an interesting case that I think, well, actually, I guess there are only two data, so one should be careful about drawing too many profound conclusions, but clearly that means more data are needed. Now let's zoom in on the planet itself. Let's look at these atmospheric or auroral ovals. And again, some fraction of that energy that is being provided by the stellar wind comes out in the UV. And yes, this is the next slide. This is the case now for HD 209458b, which is one of these hot Jupiters. And using Jupiter as a model, the team, which will be Kevin France and his team, were able to predict what should be the emission from the auroral oval, from this hot Jupiter. And in fact, there should be, as I understand it, two contributions. One is as the electrons stream down, they will produce the actual electrons impacting the molecules, the hydrogen molecules in the upper atmosphere, will produce this purple trace here, this purple spectrum. And then there'll be additional fluorescence from the starlight, the UV starlight of the star hitting the planet. And then combined, you would expect this blue curve. So this is a nice simple thing. You can make a prediction of what the planet should look like in the UV based on starting or modeling it from Jupiter. You can now, and before I do that, the pretty picture example of this is in the solar system case. Here are the auroral ovals, actually both for Jupiter and for Saturn. And you can certainly see that in the UV, the dominant emission from the planet, at least at certain wavelengths, is coming out in these magnetically generated auroral ovals, if you will. Okay, here's the case of HD 209458. Here again, this is the model. And this is now blown up. These are much smaller wavelength regions. You can see that's something like 50 angstroms. I think both of these are sort of 50 angstrom chunks from that much larger spectrum that was shown on the previous. And the interesting aspect is here are then the actual data from the HST, the COS instrument on HST, and there's no obvious indication that these expected spectral lines are showing up in the spectrum. Moreover, I think the team has done a very good job because in the case of this HD 209458, you know that at one part of the orbit, these lines should be shifted to the red as the planet moves away, and then on the other side of the orbit should be shifted to the blue. So you not only can go looking for these lines, you have an expected shift in the spectrum from the atmospheric or the auroral lines. Okay, as I just showed, for Jupiter and Saturn at least, this electron impact molecular hydrogen lines, they all come from that auroral oval, or at least they're dominated from the auroral oval. The fact that HD 209458 doesn't show these lines leads one to suggest that it either has little or no auroral oval. And the conclusion that the team draws from that is that it potentially has a weak magnetic field. And the formal number, I believe, is slightly below this, but then allowing for various uncertainties. It's something like 10%, at most something like 10% the strength of Jupiter. Finally, then, as I indicated, not only is there UV emission, but there's radio emission. That's somewhat difficult to see in these plots. But here's an actual example, again, taken from the solar system. This is the emission from Jupiter. Now, actually, interestingly, taken from the Cassini spacecraft during the cruise phase of Cassini out to Saturn. It turned on various instruments, I think, as part of a checkout. And here is now actually what is a dynamic spectrum of Jupiter. So this axis is time, actually about 10 hours, so roughly one rotation period of Jupiter. This axis is frequency, if you don't like thinking of, and frequency increasing this way, if you don't like thinking about frequency. Wavelength increases this way, or it's color. And there are a couple of things to pull out from this. First is that while here is the IO contribution, you can see that the IO contribution is very strong. The color scheme here is a logarithmic. So things that are red are potentially orders of magnitude larger than things that are blue. It's very dynamic. So you see that IO is present for a while and then it goes away. There's other emission. And in fact, I believe Dave mentioned this earlier, in many cases, the rotation period of the planet, at least for the gas giant planets, is determined from these changes in the radio emission because that's thought to be coupled deep into the interior, whereas, for instance, tracking cloud features, it's not clear what that tells you about, say, the deep interior rotation. This emission was actually discovered somewhat serendipitously by Burke and Franklin. It was one of those cases they were not looking for it. And the Earth's own emission was not recognized, as I understand it, until about the International Geophysical Year of 1957 or shortly thereafter. And that's because the emission from the Earth doesn't make it through the Earth's ionosphere. I'll come back to this point. But effectively, the Earth's atmosphere blocks the radio emission from the Earth. And it wasn't really until we had the Voyagers that the field was opened up, and we now know that all of the gas giants and the Earth produce this electron cyclotron maser radio emission from their polar regions. As in many things in science, there's nothing new under the sun. This is, I believe, the earliest attempt to do this for extrasolar planets. It's taken from the Bulletin of the AAAS, 1977. And at the time, they knew of 3 solar system planets that emitted this auroral radio emission: Jupiter, Earth, and Saturn. Nonetheless, they struck out with the, Clark Lake Radio Observatory and observed 22 stars within 5 parsecs. As I'll illustrate in a little while, their sensitivity is such that it's not surprising they didn't detect anything. But I think it was a remarkable foreshadowing, or very prescient, that even with only 3 planets in our own solar system, they were bold enough to say, hey, maybe there are extrasolar planets that emit this same thing. Also, sort of prior to what I would call the modern era, this kind of approach was repeated by another group using the Very Large Array. Why might we expect to see this kind of emission from extrasolar planets? This is a plot of the, in one case, one of the ways that a planet can generate radio emission. This is the kinetic power delivered by the solar wind, and this is the output power, or in some sense you can think of this as the radioluminosity. You can see here's Jupiter, Saturn, Earth, Uranus, and Neptune. And let me move this. This plot, there are actually several things to take away from this plot. First, of course, there are 5 data here, and for astronomical purposes, this is actually a fairly good correlation. Secondly, the plot illustrates the extent to which the solar wind, or what we might expect the stellar wind, how strong of an influence that has on the planet's radioluminosity. Earth has a magnetic moment that's less than that of Uranus and Neptune. And I think as Dave showed, its actual magnetic field strength is only comparable to, but its actual magnetic moment is less than. Nonetheless, it has a larger radioluminosity than either Uranus or Neptune. Oh, one aspect that I don't think I've mentioned, these bars here are not uncertainties. They're an attempt to indicate a range. How much does the planet's radioluminosity vary? And again, it can vary because of changes in, say, stellar wind strength. But the point is that the stellar wind, or the influence of the stellar wind, plays an important role in this, because Uranus and Neptune, although they have larger magnetic moments, are less radioluminous precisely because they're out at, 15 or 30 AU as opposed to 1 AU. Another aspect, not immediately obvious from this plot, but this plot has already been used, or these data have already been used in a predictive sense. In 1986, before Voyager reached Uranus, Mike Kaiser and Mike Desch, they only had these 3 data. They predicted what Uranus's radioluminosity would be, and in fact, the measured luminosity was smack in the middle of what they predicted. And then this was repeated later as Voyager 2 continued outward to Neptune. There was a prediction of what should the Neptunian radioluminosity be, and again, the actual measurements were smack in the middle of it. Finally, I think you can see where this is all going from an extrasolar planet perspective. This planet, Jupiter, is out at 5 AU. These planets are out at sort of 10 to 30 AU. If you start moving them in, you should expect the luminosity to increase potentially substantially. And in fact, people have been looking. This plot shows, I believe, a complete, or at least a nearly complete census of all of the radio observations, almost all of the radio observations of which I'm aware. Frequency again down here. The measurements are color-coded from the Very Large Array. So these are the blue points here, the GMRT, orange, and then the one attempted by the Green Bank telescope, actually using a method somewhat analogous to what Kepler is up there. I have not shown, for reasons that will become apparent in a minute, I've not shown the VLA has also been used at 1400 megahertz, so there are some additional data up here. This trend is due to the fact that radio telescopes, effectively their sensitivity at these frequencies or at these wavelengths is limited by how much metal you can put on the ground, or how much collecting area you have. So this trend here simply reflects the fact that we have a fixed amount of collecting area, and to be substantially better, we're going to have to build more. This point here is that's at least an acclaimed possible detection of radio emission from one extrasolar planet. It is, in some sense, it's a case of sort of like setting sail on an ocean with only 2 clocks, because what the team did was they made a measurement on 2 days and they detected radio emission in one day and didn't in the other, and they therefore claimed that, well, that might be a detection. I'll leave it to your judgment as to whether that is in fact the case. And then this actually it's an upper limit. This diamond here is in some sense a statistical detection. We took a number of different stars in the solar neighborhood and then stacked them or co-added them. I've also taken the liberty of putting up one as yet unpublished LOFAR limit. For historical purposes, there's where the Clark Lake sensitivity or measurements from 1977, those were about that. There's also a telescope, a still operational telescope in the Ukraine, but its sensitivity for various reasons is also up there. Importantly, Jupiter on this plot sits down in here. And you can see that we may have a little bit of ways to go to get to a Jupiter-like planet, although we can potentially move the curve, or we might hope to have detections up in here if the planets have, say, extrasolar planets have larger magnetic moments. And of course, as I've already indicated, if they are closer to their host star than Jupiter is, they should be pushing up in this direction. The final reason, and one of the reasons since we're at the Keck Institute for Space Studies, to put space into this, this is some indication of where the ionosphere is becoming opaque. Effectively, you can't see out of the Earth's atmosphere. And the value, you know, depending upon solar cycle and time of day, it varies, but somewhere certainly by about 30 megahertz, it starts to become a bit tough to see out. And as you go lower in frequency, the atmosphere becomes essentially black. You can't see out. Notably, Earth is not on here because it emits, as I indicated earlier, at frequencies so low that you can't see it from the ground. My penultimate slide is just coming back to this point that I believe both Greg and Evgenia have already made. I've been talking about the planet almost in isolation, but also making the comment that the radio emission, well, actually both the radio and the UV emission, is driven by the stellar wind. So in some sense, we do have some kind of coupled system, and it may be that we'll have to understand the entire system in order to draw inferences about the planet. And my flippant answer when I've given colloquy on this topic is I'd very much like to have that problem. So I will simply leave up, this is my final slide. I hope I've convinced you that there are potential ways to detect or infer the presence of a magnetic field of extrasolar planets over interstellar distances. Thank you.